The paper introduces a novel disease-specific attention-based deep learning model, DANet, designed for the detection of arrhythmias from short ECG recordings. This model aims to enhance the interpretability of deep learning models in healthcare applications, particularly in the field of ECG analysis. The proposed model incorporates a waveform-enhanced module that modifies original ECG signals based on specific diagnostic rules for a given disease type before feeding them into the classification module. The study focuses on the problem of atrial premature contraction detection and demonstrates superior performance compared to benchmark models. Furthermore, it provides insights into the waveform regions that deserve special attention in the model's decision-making process, making it a valuable diagnostic assistant for physicians. Traditional methods for arrhythmia classification heavily rely on discriminative features derived from ECG signals, resulting in unsatisfactory performance due to limitations in feature extraction. Deep learning models, such as CNN and LSTM, have made significant breakthroughs in ECG analysis and improved classification performance. However, these models lack interpretability, restricting their application and popularization in clinical practice. The performance of detecting different arrhythmia types from short ECG recordings varies widely, with lower detection accuracy for atrial premature contraction compared to atrial fibrillation using similar network architectures. This is attributed to deep neural networks treating each sampling point of an ECG signal equally, leading to the dominance of QRS complexes over P and T waves. The proposed DANet model addresses this issue by incorporating a waveform-enhanced module that adjusts the ECG signals according to the diagnostic rules for a specific disease type before classification. This approach not only improves the detection performance but also provides interpretable insights into the decision-making process, making it a promising tool for clinical practice. Physicians diagnose arrhythmias by analyzing ECG signals, focusing on specific waveform regions, such as P waves for atrial premature complexes and regions between S waves and T waves for STT abnormalities. This approach is reminiscent of attention mechanisms used in natural language processing, computer vision, and time series analysis, which selectively focus on relevant input regions. However, traditional attention mechanisms are general-purpose and data-driven, often failing to align with cardiologists' domain knowledge and decision-making processes. To address this limitation, a disease-specific attention-based deep learning model, DANet, is proposed, which incorporates cardiological domain knowledge into the ECG analysis pipeline. DANet amends original ECG signals before feeding them into deep neural networks, enabling the model to mimic cardiologists' cognitive processes in diagnostic decision-making through a disease-specific attention mechanism. Existing studies share similar design goals, including spatiotemporal attention-based convolutional recurrent neural networks, explainable deep learning models, and model-agnostic methods for heartbeat classification. While these approaches focus on feature extraction, interpretability, and performance improvement, they often rely on general-purpose attention mechanisms or data-driven techniques. The proposed DANet model aims to overcome these limitations by integrating domain knowledge into the attention mechanism, allowing it to better align with cardiologists' decision-making processes. The model is designed to provide a more accurate and interpretable diagnosis of arrhythmias, leveraging the expertise of cardiologists in the ECG analysis pipeline. The proposed DANet model is a deep learning architecture designed to detect specific arrhythmias from ECG signals, utilizing a binary classification approach. It consists of 5 processing modules: data preprocessing, manual attention weight, data augmentation, waveform enhanced module, and classification module. Data preprocessing techniques such as resampling, filtering, amplitude normalization, and lead selection are applied to the ECG data before feeding it into the subsequent deep learning modules. A traditional fiducial point method is used to find the onset and offset of every P wave, QRS complex, and T wave in the input ECG recording. Manual attention weights are set for different waveform regions based on clinical diagnostic rules and the onset and offset of each waveform component. These weights are not required for the testing phase. Data augmentation strategies like picking random ECG segment and adding random noise are employed to improve the generalization ability of the model. The waveform-enhanced module utilizes prevalent network architectures such as dilated convolutional neural network and UNet to extract features from the ECG data. This module outputs automatic attention weights through calculating each internal node state in forward propagation pass. The model needs to be trained in advance, using a loss function concerning manual and automatic attention weights. The Deep Attention Network (DANet) framework is a multimodule architecture consisting of a waveform-enhanced module and a classification module. The waveform-enhanced module is trained in a self-supervised manner using traditional fiducial point methods to obtain attention weights, denoted as W1K, without requiring physician engagement. This module identifies specific ECG wave regions with clinical diagnostic significance, such as P-wave, QRS complex, and T-wave. The classification module, implemented using existing deep learning models like VGGNet or DANet, outputs the final detection result. Unlike conventional approaches, the ECG data is first multiplied by automatic attention weights, denoted as W2K, using a sampling point-wise operation, incorporating cardiological domain knowledge into the model. The resulting ECG data is then fed into the classification module to calculate class probabilities. To prevent model overfitting, a two-stage training method is employed. In the first stage, the waveform-enhanced module's parameters are frozen, and the classification module is trained in an end-to-end manner using backpropagation. In the second stage, the entire model is fine-tuned in an end-to-end fashion, alleviating the limitations of traditional fiducial point methods. During testing, automatic attention weights provide valuable reference information beyond detection results. For instance, if the attention weights do not focus on the region between the S-wave and T-wave, the detection result of STT abnormalities is deemed meaningless. The core idea of DANet is to leverage cardiological domain knowledge to treat different ECG wave regions differently, enabling the model to predict accurate detection results. The Deep Arrhythmia Network (DANet) model consists of two primary modules, a waveform-enhanced module and a classification module. The waveform-enhanced module utilizes a dilated convolutional neural network with residual connections, enabling accurate localization of P-waves, QRS complexes, and T-waves in ECG signals. The dilated convolution effectively expands the receptive field without increasing computational burdens. The classification module can be either a classic convolutional neural network or a local pattern aggregation-based deep learning model. To construct the DANet, various strategies are explored, considering factors such as single-lead ECG signals, shared network models, and computational burdens. A novel lead attention module is introduced, designed to strengthen or weaken feature information derived from specific ECG leads. This module can be pre-trained using manual lead attention scores and fine-tuned with the waveform-enhanced and classification modules. Model interpretability is crucial in healthcare applications, particularly in understanding which waveform regions the classification module focuses on for a given disease type. The automatic attention weights provided by the waveform-enhanced module offer valuable insights into these regions, enhancing the clinical significance of the proposed DANet. In the proposed framework architecture, the waveform-enhanced module plays a vital role in ensuring accurate detection results, even when the final detection outcome is correct. This module facilitates model interpretability by providing automatic lead attention scores, enabling the ranking of lead importance and validation of the final detection result. The DANet, a deep learning model, utilizes soft coding attention of ECG waveforms, comprising a routine classification module and a waveform-enhanced module. The latter extracts every P-wave, QRS complex, and T-wave in ECG signals and possesses adjustability characteristics. However, traditional fiducial point methods, such as ECG PU-wave, may not accurately identify PQRS T-waves, leading to incorrect manual attention weights. To address this, the pre-trained waveform-enhanced module can be updated in the later training stage. In contrast, a routine deep learning classifier can achieve better performance using amendatory ECG signals obtained with manual attention weights as inputs. This hardcoding attention of ECG waveform-based model, referred to as DANet, does not require a feature extraction-oriented deep learning model, resulting in lower computational burdens. However, it relies on external software packages, such as ECG Wave, and manual attention weights, which do not leverage data-driven technologies. The internal schematic diagram of the proposed DANet is illustrated in Figure 3, where the convolutional neural network serving as the classification module can be replaced by any existing deep learning model to process fixed-length or variable-length ECG signals. The authors apply the proposed DANet and DANet models to the atrial premature contraction (APC) detection task using single-lead short ECG recordings. APC detection is crucial in clinical practice, as it is a sign of disturbance in the depolarization process preceding atrial fibrillation and supraventricular tachycardia. The authors provide details of the experimental implementation and present the results of a comparative study. This research paper presents the development of a novel deep neural network, DANet, for the detection of atrial premature contractions, APCs, in electrocardiogram, ECG, signals. The authors employed a two-stage approach, combining a waveform-enhanced module with a classification module to enhance accuracy. An attention mechanism is introduced that highlights regions of interest in the ECG signal, improving the network's ability to identify APCs. The dataset used is the Alian Tianqi ECG Challenge Database 2019, comprising 32,142 8-lead ECG recordings. The training dataset consists of 689 APC recordings and 10,174 non-APC recordings, while the testing dataset includes 762 APC recordings and 11,284 non-APC recordings. A validation dataset was created using 75 APC recordings and 1,122 non-APC recordings. ECG signals were preprocessed by downsampling from 500 Hz to 150 Hz and applying a 6-order bandpass filter with a cutoff frequency of 0.5 Hz 50 Hz. The onsets and offsets of every P-wave, QRS complex, and T-wave were identified using the open-source software ECG Wave. The attention weight was set to 1 for sampling points located in wave regions and 0 otherwise, as shown in Figure 5. A 9-layer classical convolutional neural network was used as the classification module in both the DANet and DANet models. This network consists of 3 alternating layers of convolution and max pooling, followed by a multi-layer perceptron composed of a fully connected layer with 50 nodes and a logistic regression layer. For the DANet model, an 8-layer dilated convolutional neural network with residual connections was used as the waveform-enhanced module. This module includes 4 dilated convolutional layers with 6 filters, a kernel size of 9, and a dilated rate of 7, along with 1 convolutional layer with 1 filter and a kernel size of 1. Residual connections were applied between the left and right branches of each even dilated convolutional layer. Both the DANet and DANet models were trained in an end-to-end fashion using the Atom optimizer with default hyperparameters and a mini-batch size of 256. The DANet model utilized binary cross-entropy as the loss function and was trained for 100 epochs. The remaining sections of the paper will likely detail the experimental results, discuss the performance of the proposed models, and outline potential future directions for this research. The research paper presents a comparative analysis of various deep learning models for detecting atrial premature contraction, APC, in electrocardiogram, ECG, signals. The proposed model, named DANet, consists of 2 main components, a waveform-enhanced module and a classification module. The waveform-enhanced module utilizes a soft-coding waveform enhancement technique to improve the quality of ECG signals by amplifying wave regions, which are crucial for APC detection. This module is followed by a classification module that uses a 9-layer convolutional neural network, CNN, to classify the enhanced ECG signals into different rhythm types. The evaluation of the proposed model was conducted on a dataset containing 11,000 ECG recordings from 11,000 patients. 3 training stages were employed, with the second stage yielding the best results. The Stage 2 DANet model achieved an accuracy of 89.15%, sensitivity of 54.33%, specificity of 91.50%, and FS scores of 38.78%, 94.05%, and 66.41% for APC, non-APC, and overall rhythms, respectively. These results outperform the standalone CNN model, demonstrating the effectiveness of the proposed waveform enhanced module and DANet-specific attention mechanism. The paper also discusses the limitations of traditional deep learning models in ECG analysis, particularly their lack of interpretability and focus on QRS complexes rather than non-QRS complexes such as P waves and T waves. The proposed model addresses these issues by incorporating a DANet-specific attention mechanism that highlights the importance of wave regions in ECG signals for APC detection. The findings suggest that the DANet model can provide valuable insights into the inference process of deep learning models, enhancing their interpretability and performance in healthcare applications. The attention mechanism in deep learning models can treat different regions of an ECG signal differently, but existing schemes often discard domain knowledge and rely solely on data-driven technology to obtain attention weights. This may lead to a loss of interpretability and potentially incorrect diagnoses, as statistical features extracted by deep learning models may not necessarily correspond to clinically relevant features of ECG waveforms. In contrast, the proposed DANet incorporates domain knowledge into the attention mechanism to mimic the diagnostic process of physicians in ECG interpretation. This is achieved by transferring knowledge from ECG PU wave to a waveform enhanced module through self-supervised pre-training and associating attention weights with rules for diagnosing cardiac diseases. The waveform enhanced and classification modules are then fused and fine-tuned in the final training stage to compensate for defects induced by ECG PU wave. The novelty of DANet lies in its ability to represent diagnostic rules for a given disease type explicitly through attention weights, rather than ambiguously. This approach enhances the effectiveness and robustness of deep learning models and provides a degree of model interpretability, where attention weights implying domain knowledge are always presented alongside detection results. The proposed DANet is validated through a case study on APC detection, demonstrating improved performance compared to benchmark models. Additionally, experiments show that DANet can also improve detection performance for STT abnormalities. Future work involves extending the model to detect other arrhythmia types from ECG signals. This research paper provides a comprehensive review of deep learning models applied to electrocardiogram, ECG, analysis for arrhythmia detection and classification. It discusses various state-of-the-art techniques that leverage attention mechanisms, knowledge fusion, and multiscale context aggregation in their architectures. The paper begins by highlighting the importance of ECG analysis in cardiac disorder diagnosis and the challenges associated with interpreting ECG signals. It then delves into the concept of long short-term memory, LSTM, networks, which are commonly used in sequence-based data processing tasks like ECG signal analysis. Attention mechanisms play a crucial role in enhancing the performance of deep learning models in ECG analysis. Studies have successfully employed attention mechanisms to improve the accuracy of arrhythmia detection and classification. For instance, the multitask channel attention network, MCA-net, proposed by Wang et al., uses domain knowledge to guide the model's attention towards relevant features in the ECG signal. Knowledge fusion techniques are also discussed as a means to incorporate domain knowledge into deep learning models. This approach aims to leverage expert knowledge about ECG signals to enhance model performance and interpretability. The knowledge-driven graph convolutional network, KDGCN, is cited as an example of such a method, which integrates graph convolutional networks with domain knowledge to improve abnormal ECG diagnosis. The paper also touches upon the concept of multiscale context aggregation, citing the work of Yu and Colton. This technique involves applying dilated convolutions to capture contextual information at different scales, potentially improving the model's ability to recognize patterns in ECG signals. In conclusion, the paper emphasizes the need for further research in this area, particularly focusing on improving model interpretability and incorporating more domain knowledge into deep learning architectures. Future studies should explore novel ways to integrate expert knowledge and attention mechanisms to enhance the accuracy and reliability of ECG analysis models. This page presents a comprehensive list of the key findings and implications from the study. The research has demonstrated that the proposed methodology significantly improves the accuracy and efficiency of data analysis in complex systems. The study's primary focus was on developing an innovative algorithm capable of processing large datasets with enhanced precision. This algorithm, named DataProc, utilizes advanced statistical techniques to identify patterns and trends within the data, providing researchers with valuable insights into system behavior. One of the most significant findings of this study is the ability of DataProc to reduce computational time by up to 40% compared to traditional methods. This reduction in processing time allows for quicker analysis and decision-making, which can be crucial in time-sensitive research environments. Furthermore, the study highlights the robustness of DataProc in handling noisy data. By employing advanced noise reduction techniques, the algorithm is able to effectively filter out irrelevant information, resulting in more accurate results. In addition to its technical contributions, the study also discusses potential applications of DataProc across various fields. For instance, it could be used in financial markets to analyze stock market trends, or in healthcare to identify disease patterns from patient data. However, the study also acknowledges several limitations. For example, DataProc requires a high level of computational power, which may not be readily available in all research settings. Additionally, the algorithm's performance may degrade when dealing with extremely large datasets. Future work includes addressing these limitations and further refining the algorithm to improve its efficiency and applicability. The authors suggest exploring distributed computing methods to enhance computational power and developing new statistical techniques to handle larger datasets. Overall, the study presents a promising new approach to data analysis that could revolutionize the way researchers process and interpret complex datasets.